channel bandwidth. And what we had said was case 1, or what we had shown was if then there is this is where we stopped, right? So now let us look at the case with Nyquist sampling, or rather Nyquist pulse shaping. We see that right?
Yes, sir.
Or rather, we know that right? We have derived, we know this about the sync function. So
Yes,
this
sir.
is good, but there is a problem. Sync function is non-causal. Agreed?
Yes, sir.
And 2, it decays as 1 over t, or 1 over t, or yes, it decays with 1 over t time. So decays slowly, which is not good. Which means that I can.
So small t, right?
No, capital T.
So it is 0 at xmt, and
So it's T over T, sync. Oh yeah, small t. Right. 1 over T. Decays with capital T over small t then. No. See, sine pi t by pi t by t divided by, this is it, right?
Yes, sir.
So decays like this. So of the t by delaying the symbols by some delta, but effect of that depends on the rate of decay, right?
Yes, sir.
So the faster this decay is, the better. So we go with practically instead go with slower than Nyquist signaling and call it raised cosine signaling. Now case of raised cosine signaling, RC stands for raised cosine. Okay, so this zero. Fine. So the first thing we notice, do you hear that humming sound?
No, sir.
Yes or no? So louder.
No, sir.
Okay, good for you. I don't know. There's a strange humming sound in my office for some reason. Yeah, we notice that this has now it has stopped. Maybe there is some construction going upstairs. So this is suboptimal in terms of bandwidth, and this alpha, or rather 1 upon 2w, I would write it this way: w equal to 1 upon 2t plus alpha. Right, alpha, or the roll-off factor, and indicates the extra bandwidth occupied by the signal to prevent beyond the minimum required bandwidth. Fine. And from here, it is easy to show that this is just a lot of mathematical jugglery, so I won't be doing this. Cos phi alpha t by t divided by 4 alpha square t square by capital T square, and this decays as, or rather, t by t cube by t cube. Fine. You can try taking the inverse Fourier transform. It will take a couple of hours. That's why I'm not doing it. Or it will take a lot of time. That's why I'm not solving the Fourier transform here.
So shouldn't it be t square?
Sync also has a 1 over t.
Oh, multiplied. Okay.
Yes. So, these are multiplied. Not convolved, multiplied. Fine. So in general, want XRC equals GF right?
Yes, sir.
And if we are lucky and the channel CF is flat within the of or within the bandwidth of interest. You note that since this is being multiplied by sinc t over t, this will be 0 at all the places of interest. Because this entire thing will be 0 when sinc t over t will be 0, right? That is always there. But this will also be non-causal within the band of interest. Then GF equals root over x. Just take the square root j 2 pi f delta, where delta is the delay compensating for non-causality of the pulse. Fine. Similarly, PF, since the channel is flat, this is fine, times some delay. This will give you raised cosine pulse shape or raised cosine spectrum.
Yes, sir.
Yes, now we consider case where channel is non-flat as a response CF. Then we have two possible designs. One, GF equals F CF F delta, not delta F. This is one possible design.
Yes, sir. So
The
that
other
is
possible design is, oh, sorry, wait a
CF.
second. PF equals, I have to complete this. This is one possible design.
So there won't be a square,
There won't be a
right?
square inside. Yes, just this. Fine, this is one possible design. The second possible design is sorry, this has to have that minus j2 pi f delta. This and PF is fine. Both of these, the receive PF will be the matched filter. Fine. Any guesses on which one will we use?
So the first or second one.
The second one. Why is that?
Because in that we have to, I mean, the PF is constant and we have to only change the GF. The constant as in we, if we know the X or CF.
So I didn't get that, Adit. Can you?
Sir, because uh, I mean, GF is on the side of the receiver, sorry, sender,
No,
right?
GF transmitter.
Yes, the transmitter.
Yes.
So that, I mean, once we know how the channel looks like, we can control GF uh, much more easily than we can control the transmitter side PF. Oh, sorry, receiver side PF.
No, actually, it's easier at the receiver controlling. There is something else. So I'll give you a minute to think. I need a minute's break, and then I'll come back and answer. Fine?
Okay, sir.
Yeah, just a minute. Yes. So I'm back. Any better guesses?
Sir, we don't know the exact CF, right? We only know the estimate of the CF.
That would be true in both the cases.
No, sir, but isn't it easier to estimate the CF at the transmitter end?
How? So that is a separate question, but generally you receive the signal at a receiver, right? So estimation will always be easier at the receiver than the transmitter. Isn't it so?
Yes, sir.
So you receive at the receiver, you don't receive at the transmitter, and you always estimate using the received signals. Make sense? So let's look
Yes,
at
sir.
this in the time. Yeah. Let's look at this in terms of the received signal. So YF, or rather case 1, rather I would write first like this. So YT equals GT convolved with CT convolved with PT right? If I forget about the information symbol for a second.
Yes, sir.
We are missing one thing. Now, right?
Yes, sir.
Yes. So see, RT is GT convolved with CT plus WT, and you convolve the entire received signal with PT. That's what you do, right?
Yes, sir.
Yes. So now SYYF, or yes, S small y, actually it should be YYF equals PF CF GF plus whole square. Actually, this thing whole square plus N naught by 2 times right.
Yes,
Agreed.
sir. Yes, sir.
So this noise you see is non-white or colored noise. Now case 1
Sir, won't
S,
there be another term containing both the terms 2 into PFCF, GF, and
sorry, both the terms.
I mean, when you do SYIF, we are taking the modular square of the entire RYY.
The see power spectral density is the Fourier transform of the autocorrelation function. There is no frequency domain definition of power spectral density.
Yes, sir. But when we take
So
the cross,
let me, and noise and the signal are uncorrelated.
okay, sir.
Fine. So that's why I do not define the power spectral density in the frequency for noise. Noise is a random signal. If you remember in the last semester, we spent a lot of time developing these frequency domain representations or frequency domain interpretations of random signals. Remember?
Yes, sir.
Yeah. That's why we do not use that multiplication or those things here, because frequency domain multiplication, because it's hard to characterize random signals in terms of their frequency domain components. In cyclostationarity, I developed a special case where I took the expectation of the frequency domain. That is something quite different. You have to look at Gardner's book for a detailed discussion on that. But yeah, so this is the way it is. Now, in case this happens, in case this is now case 1, yes, SVVF equals N naught by 2 right? Case 2. The this part remains the same in both cases.
Yes, sir.
The second part is the only thing that changes. This will anyway reduce to XRC F. This part is same in both the cases.
Yes, sir.
Yes. So now here it's a case 2. If I look at it, I get a colored noise. I get colored noise, but so the flat power spectral density of the noise gets multiplied with something like this, and I know the noise spectrum, but the channel is arbitrary and can have a frequency response looking like not negative, something like this. Fine. The channel can have a frequency response like this. Nothing stops it from having such a frequency response. You would agree on that?
Yes, sir.
So now at this point, CF is the arbitrarily small, which means 1 over CF can be large, right? 1 over CF can be arbitrarily large,
Yes, sir.
which means for a channel with, or for a part of the channel with a poor frequency response, the noise can get agreed.
Yes, sir.
So, and now you would know that why I didn't consider a third case where there was nothing in the transmitter and the full channel in the receiver. You
Yes, sir.
you must have thought that there could be a third case as well. Why isn't this guy considering that? So yeah. So this is about how we try to control ISI in band limited channels. But the thing is, we can not always totally control it without complicated signal processing tricks. So if we cannot control it, the next part of the story is learning live with. cannot control the coronavirus, you shift everything to the online mode, right? So how do we learn to live with ISI? So the first parameter is to try, or the first way of doing this is, or there are multiple subtopics that is, one, how can we use our advantage? Two, how does this affect the system performance? Can we remove ISI once we get it? Completely different. Fine. So these are the topics in this chapter that we are still left with. So I'll cover them one by one. The first of these is partial response signaling, or how to use ISI to our advantage. So this now for 0 ISI had the condition that let us relax this condition and manually introduce some I have introduced some ISI, right? Therefore, Zn equals with Nyquist pulse shaping. Or at the Nyquist rate. Fine. This is called the duobinary pulse. We'll come to the details in a minute. Another form of controlled ISI is the modified duobinary pulse shape. Pulse. Where and this using similar jugglery, you can show that
So that is sine or okay.
sine. Similar. Using similar steps, you can show that this is there. So now, how do we achieve this? To achieve this, Bm equals plus four and four and fine.
Okay, so
Yeah. So let's discuss the case of duobinary. Sing duobinary pulse shapes or duobinary shaping with no residual ISI. So now Ym equals Bm plus we used V right? This is right.
Yes, sir.
Yeah, awesome. So since this is right, what is this? We have encountered this kind of a signal earlier, or this kind of a received signal earlier. What is this? So Ym, you see, depends on Bm, and therefore depends on Im, and so partial response signaling introduces controlled ISI, but it also makes Ym. What does it make Ym? Come on.
Sir, a moving average.
You have gone too far. Signal with memory. You discussed signals with memory.
Yes, sir.
Moving average processes are something different. Different course. Yeah. Makes Ym signal with memory for Am in plus minus 1 Bm. Bm can be plus 1, plus 1, 2, plus 1, minus 1, minus 1, plus 1. Right? So Bm equals
So that should be 2, right?
sorry 2 by symbol. We can detect the symbol by symbol, but in symbol by symbol detection, if we have an error and the error is followed by string of zeros, then the error will tend to right? The error will tend to propagate.
Yes, sir.
So the error will tend to propagate. So how do we solve this? One, construct a state diagram and trend list. So we actually see that in this case, there are three possible states. If you start with 0, if you start by a 0, so a 0 means a -1. So then you actually don't start at a state. You actually have two initial states. If you start, the first symbol is always 0, then you either start at 1 or -1, or you could start, the second symbol can either be 1 or -1. So you start either at a 0 or a -2. So then, and from 0 you can go to +2. You can stay at 0, or but from this 0, yeah, you can this, or and from this 0 and from this -2 you can either go to 0 or you can stay at so 0, -2, +2. So you have a 3-state trellis where you, so T, 2T, 3T, you will have a 3-state trellis where you can go from either of the two states to 0, but cannot go from, but you cannot go from -2 to 2 or 2 to -2, right? Make sense? Or any problems with this?
So why can't we change from -2 to +2?
-2 to +2, you cannot go directly because -2 corresponds to -1, -1 or 1, 1. So now if the next symbol is, so let's say -2 corresponds to -1, -1, right? So if the next symbol is -1, you stay at -2. If the next symbol is 1, you go at 0. There's no way you can go at go to 2 from -2.
Okay, sir.
Similarly, the other way around. Fine. So you construct a trellis and try to recover this using the Viterbi. Fine. You construct a trellis and try to recover this using the Viterbi algorithm. That is one way of doing things, and that is why Viterbi algorithm is so important. The other way is you hack into the partial response signaling, or you hack into duobinary signaling further and hack into duobinary signaling further use pre-coding, that is precondition or pre-prune or pre-groom the transmitted data so that can work the received symbols can be seen as standalone. At reception. So how do we do this? Say define PM equals IM or not IM, DM modulo M, or in case of binary modulo 2 addition PM minus 1 as the mth bit being encoded. The mth bit being sent via to a binary. The mth information bit and IM equals -1 if PM equals 0, 1 if PM. Fine. Or rather, IM equals 2 PM minus 1. Fine.
So DM can take values 1 and -1, right?
DM 1 and 0. Bit. DM is a bit.
Okay.
So DM fine. So yeah. So now what is modular 2 addition? What is it?
Sir, we add PM minus 1 and then take the remainder with 2. To ensure that PM is a... Oh, okay.
Fine. Isn't it the XOR operation? So, because, oh, you haven't done coding or you haven't done Galois fields. Galois, I don't know how to pronounce French names. Galois, whatever, fields in information theory.
No, sir.
Oh, that's sad. Because, oh, so what I will do is I will continue as long as the laptop battery lasts. Because if I plug it in, I won't be able to write. We'll try plugging it in. Modular to addition is XOR, and so now oh, it's working. Nice. BM equals not working. Working, great. Equals to PM plus 2 PM minus 1 plus 2 PM minus 1 minus 1. Equals 2 PM plus 2 PM minus 1 minus 1. Let's move on to right.
So minus 2, right?
Yeah, minus. Yeah, so, oh, sorry. This. Or PM plus PM minus 1 equals BM by 2 plus 1. Right?
Yes, sir.
Also, DM I'll move on to where? Where should I move? Cornered. So I will create a box. I'll create a box here and right there. So, but DM equals PM XOR PM minus 1 since PM equals PM minus 1 XOR DM. So you know the way XOR works?
Yes, sir.
So using XOR, this is true. And from this, since PM plus PM minus 1 is a binary number, thankfully, I can replace PM. So this will either be 0 or 1. PM plus PM minus 1, which will be the same as PM XOR PM, and therefore DM equals gone. So the battery is over. We'll stop here then.
Okay, sir.
Okay, and let's see. So Tuesday no class. Wednesday I'll let you know. Maybe next Friday, if you can squeeze in 1 hour, I'll be happy. Fine. Okay, guys. So next week, actually, next week, Wednesday, Thursday, Friday, anytime you can squeeze in 1 hour, let me know. Fine.
Sir, your voice was not audible.
Yes.
The last thing I heard was Wednesday.
Yeah. So what I was saying is that Wednesday, Thursday, no class on Tuesday. Wednesday, Thursday, Friday, anytime you can squeeze in an extra class on these days, let me know. Fine.
Okay, sir.
Over and above the regular class, over and above the regular classes, anytime you can squeeze in extra classes, let me know. Fine. Yeah. Bye. Have a nice day, all of you.